Howdy everyone, welcome for the chapter 19 example problem video. Here we'll be looking at spontaneity, entropy, delta G, and a little bit of its connections with equilibrium, kind of hitting some of the major points. I'm not going to go over calculating delta G from the enthalpy and entropy numbers too much. There is one problem, but when it has you calculate delta H, it's still products minus reactants just like it was in chapter 5. When it asks you to calculate the delta S from the entropy values in the back of the book, it's still products minus reactants, just like in chapter 5. It's just now it's the entropy numbers instead. So I'm going to leave that stuff as taken for granted, but we'll focus on the delta G Gibbs free energy, how it comes from those others. But first we are going to start with an entropy problem, not with numbers, but we're just predicting it, saying if we don't have numbers, can we say whether it will be positive or negative? And so if we just remind ourselves, a positive delta S indicates that there's more disorder, which is usually because there are more gases. And if we get a negative delta S, that means we have less disorder, which means there are fewer gases. So when we look at reactions, a lot of times we can predict whether it's going to be a positive or a negative number without doing any math other than count the number of gases that we see. And so in 1951, it does actually have you do the math, and then it says account for the sign, whether it's positive or negative. We're just going to do the sign and say, no, we can predict it without looking at them, but everything matches up. So in A here, we say, okay, in our reactants, we've got two gases, because there's a gas, there's two. Over here, there's only one gas. That means, hey, we've gone from two gases to only one. We now have fewer. That means our delta S will be less than 0. It'll be negative because we've lost gases. We've lost disorder. For B here, we're starting with one gas, but because of balancing here, we're ending up with two. We now have more gases. That means more disorder, so this delta S will be positive. If we look at or letter C, we're starting with a solid, so there's 0 gases, but we end with a solid and a gas, so we go from 0 to 1. We've increased the number of gases, so again, delta S will be greater than 0. And then for letter D, we start with 1, 2, 3, 4, 5. We start with 5 gases, but we end with 6. And so there, again, we have more gases, more disorder. We're going to expect delta S to be greater than 0, to be positive. Sometimes you might get a problem where it's like 2 gases go to 2 gases. In that case, you probably have to look up the numbers. There can be some weird ones if you get some really, if you pick your compounds just right, you might get something weird to happen. But in general, that's all you need to do to predict delta S. Just say, do I have more gases or fewer? Now, if there's no gases at all, then you move on to liquids. Do I have more liquid, more aqueous, or fewer versus solids? But gases are pretty much always the most important thing, so that's what we go to first. So that's how you do something like 51, just predicting the sign. All right. If we look at number 55, so they're giving us numbers. They give us a delta H. They give us a delta S. And so we're just going through and using these numbers correctly. So for A, it says, is it endo or exothermic? That's a chapter 5 question. That's just saying, hey, look at your delta H. It's a negative delta H. That means heat is released. It's an exothermic reaction. Now for part B, is there an increase or decrease in the disorder? Is entropy going up or down? Well, it says it's a negative entropy. That means we have a decrease in disorder. So those two answers you get just from the signs of the two numbers. All right, now for calculating delta G at 298, here we will use our new favorite equation that delta G is equal to delta H minus T delta S. Temperature must be Kelvin, which good news for us it is. So we just plug in our numbers, 35.4 kilojoules minus 298 Kelvin times negative 85.5 joules per Kelvin. Now the only thing to watch out for, notice enthalpy is kilojoules, but entropy is joules per Kelvin. So when you multiply this, you've got to make sure that you make those units match up. So times 298. And so for this term is negative 25,479 joules. But hey, we got to make it kilojoules to subtract. So we'll just move that decimal 3 spots and make it kilojoules. Negative 25.479. But it's minus that. So if we get this, then delta G negative 35.4 kilojoules plus, because our negatives cancel it out, 25 point, we'll just call it 5 kilojoules. All right, so 35.4 negative plus 25.5. We get, decimal point was not hit correctly there. 4 plus 25.5. Yeah, negative 9.9 kilojoules. And then we use that answer from part C to answer part D. Is the reaction spontaneous for these conditions? Simple answer is if it's negative, yes it is. If it's positive, no it isn't. We have a negative answer, negative 9.9. So yes it is for these conditions. And that's how you do a problem like number 55. And this is a very common one of get a delta H. Sometimes it's given to you, sometimes you got to do products minus reactants. Same thing for delta S, but once you've got them, you can say endo or exothermic, increase or decrease in disorder. You can plug in a temperature and get your delta G, and from that, is it spontaneous or not? All right, number 63. Now this one's more conceptual. It's saying determine when it's spontaneous. So there are certain conditions with delta H and delta S where a delta G will always be spontaneous, no matter what the actual values are, just depending on the sign of delta H and delta S. And then if you have the opposite signs, there are conditions where it's never going to be spontaneous. But then there are the two conditions, depending on the signs, where, well, depending on your temperature number, depending on the actual numbers, sometimes it'll be negative for certain temperatures, and then as temperature keeps increasing, it'll switch, or vice versa. It won't be spontaneous, but as you heat things up, yes, it will. So we're going to look at these numbers and say, okay, based on what we've got, again, using our delta G equals delta H minus T delta S, we're going to say, does it get more or less positive as the temperature changes? So if we look at A, where we're doing the synthesis of nitrogen plus fluorine to nitrogen trifluoride, our delta H is negative, and so if we say, oh, we plug in a negative number here, yeah, that'll help that be spontaneous, yeah. Oh, but delta S is negative. What's a negative times a negative? That's going to become positive. So the larger the temperature is, the more positive this becomes. So this will be spontaneous at low temperatures. You know, if we actually plugged in numbers, we could figure out what that maximum temperature was. But we're just going to say, no, as long as T is small enough, this will still be negative. But if T gets too big, then this whole term gets too positive, and delta G becomes positive. All right. For this one, delta H is positive. Okay, so that's going to be a positive delta G to start with. Delta S will be negative, but times the negative, that's positive. These two terms will always be positive with these numbers. So if this is always positive and this is always positive, then no matter what the temperature, it will always be a positive delta G, so it will never be spontaneous. So it's just never spontaneous for positive negative. If you go vice versa, if it's negative positive, that's when it's always spontaneous. All right, and then letter C, a positive delta H, so that leads towards a positive delta G. Oh, but a positive delta S, more disorder, which will become negative when we multiply it by the temperature. Oh, so if the temperature is high enough, then this second term gets more and more negative, and eventually delta G will become negative. So in this case, because of this delta S, it'll be spontaneous at high temperatures. We don't know where, we'd have to plug it in and calculate, but eventually with a high enough temperature, we would become a negative number. And that's what we're looking for. So that's how you do those. You just say, hey, if I plug in a positive, what does that do for delta G? Oh, it's also positive. You just kind of walk it through mathematically. All right. Number 83. This will be our last one where we're connecting delta G to the equilibrium stuff from our last three chapters, 15 through 17, where we say, okay, we've got the equilibrium of nitrous acid dissociating in water, and they want us to do a couple things with it. So first, they want us to write the dissociation reaction. So okay, HNO2, weak acid, so it's in equilibrium with H plus and NO2 minus. These would all be aqueous. There we go. They want us to calculate then our standard delta G from the Ka. So note that little degree sign, little naught there. That means standard conditions. And so at standard conditions, delta G naught is equal to negative RT natural log of K. And so we just plug those in. Now R in this case, because delta G is an energy, we want the gas constant in terms of energy. So this will be negative 8.314 joules per mole Kelvin. All right. We'll multiply it by the temperature. So it's standard conditions, so that means 298.15 Kelvin. And then we'll plug in the natural log of K. Well, they gave us the Ka in the problem, or well, looked it up from the appendix. So 4.5 times 10 to the minus fourth. So now we just plug this all into our calculators. So 4.5 times 10 to the negative fourth. Take the natural log. It's set negative 7.706. We'll just leave it there without rounding for now. We will multiply by 298.15 Kelvin. We will multiply by 8.314. And then we'll multiply by negative 1. We'll flip that sign because that negative in front. And what we get is 19,102 joules per mole, because right, the Kelvin's crossed out, but joules per mole stayed. Now delta G's are normally given in kilojoules per mole, and with a number this large, you can kind of see why. So we'll divide that by 1,000, and it looks like we have 2 sig figs. So we'll just say that this equals positive 19 kilojoules per mole. And that makes sense because a positive delta G means it's not spontaneous. It means the reaction should mostly be reactants. Well, that lines up with a K that's less than 1. K that's 10 to the negative fourth. Well, that's much smaller than 1. That favors reactants. Should be mostly reactants. So that's kind of how you tie these numbers together. Say, does my answer make sense? Did I make sure my negative sign was accounted for? This K favors reactants. This delta G, being positive, favors reactants. It lines up, so we're pretty good there. All right, letter C. What is the value of delta G? And notice this is not the standard delta G. This is just at the moment delta G. What is that value at equilibrium? Well, at equilibrium, neither the forward or reverse reaction is favored, right? It's at equilibrium. The rates are equal for forward and reverse reactions. And so by definition, the delta G at equilibrium is equal to 0. It doesn't favor making more reactants. It doesn't favor making more products. It says, nope, stay right where you are. That's what 0 delta G means. So kilojoules per mole, just to be complete. But that's a definition. Delta G at an equilibrium is always equal to 0. All right, but now what is the value of delta G when we have these conditions? So we're not at equilibrium. They just gave us some numbers. For this, we use our equation that says the momentary delta G, right, at this moment, it will always start out equal to our standard delta G, which, hey, we just found, that's convenient, plus RT natural log, not of K, of Q. It doesn't ever let me get my eraser. There we go. Eraser. Natural log of Q. Because remember, same Q as chapter 15. It's our momentary concentrations, our snapshot concentrations when we're not necessarily at equilibrium. So we plug in what we've got. We've got our standard delta G. We just found that to be positive 19 kilojoules per mole. We'll then plug in R again. So that's 8.314 joules per mole Kelvin. We'll plug in our temperature. I don't know if the temperature was given to us, but we'll just assume that it's 298.15 Kelvin. I believe that's a, say if something is 83. Yeah, it doesn't give us a temperature, so we're just going to assume that the 298 Kelvin there seems safe. And then natural log of Q. So, okay, we got to do products over reactants. So products are H plus. So we have 5.0 times 10 to the minus 2. We have the nitrite, 6.0 times 10 to the negative 4. All of this over the HNO2, so 0.20 molar. All right, so we're going to just have to start simplifying. So we take those concentrations, 5 times 10 to the negative 2 times 6 times 10 to the negative 4, all divided by 0.2, so that's 0.00015. Take the natural log of that, so it's negative 8.8048, and continuing on from there. Multiply it by the temperature, 298.15. Multiply it by R, 8.314. We get an answer that's negative 21,825. We'll go ahead and make it kilojoules. So we'll say that this is positive 19 kilojoules per mole. And it will be actually minus, in this case, how many sig figs? 2 sig figs. Well, actually it would be 3 because the natural log, the first number doesn't count, but whatever. Minus 21.8 kilojoules per mole. This is going to equal a negative 1.8 kilojoules per mole. Or, wait, is that? No, sorry, negative 2.8. Negative 2.8. And so that's saying, hey, at this point, we've actually got a little bit too much product, a little bit too much reactant, not quite enough product, a little bit more of that acid needs to dissociate. So we'll just go ahead and double check that answer just for completion's sake. That's 83. Yeah, they got negative 2.7, so they rounded a little bit differently, or maybe they kept the delta G. Oh yeah, they put 19.1. Excuse me, 19.1 for their delta G standard, so that's why they're off by 0.1, but that's all right. So that's how you do that one. So keep in mind, this is the important part. Oh, didn't mean to hit that. But the delta G naught, right, this standard, that's just negative RT ln of K. When you need to know a given delta G for a given time, that's where you say, let's start there, but then we adjust. And then at equilibrium, then, if delta G naught is negative RT ln of K, and then this is positive RT ln of K, well, that's why at equilibrium it equals 0. These two terms cancel out at equilibrium. All right, so I hope this was helpful for chapter 19. We're almost done. We're in the home stretch. So use this. Make sure you're keeping track of delta G's, what they mean when it's positive versus negative, and you'll be fine. All right, have a good day. See you soon.